It's really a pleasure to be here today to talk about one of the topics that I've been really working a lot on over the last couple of years, which is the analysis of movement data, and particularly the exploratory analysis of movement data. We've all come to be used to all kinds of fancy visualizations of movement data in media, in films, in even just company reports. So whenever we see something like this, which represents, in this case, the movement behavior in London by bicycle sharing rides, then we feel like, okay, yes, that it looks really interesting. That's what we expect to see when it comes to movement data nowadays. There is patterns in there. We are sure that we can extract some knowledge from that. Of course, it always also raises questions, but in general, as a public audience, we expect this level of visualization and of communicating interesting stories with data. This movement data is not just available in cities, obviously. There's also a lot of movement data on a grander scale. For example, movement of ships are tracked globally. And here is just a tiny excerpt from the Gulf of Finland, which a friend of mine, Topi Tukanov, created using the Time Manager plugin, which Martin already mentioned. So even over watching only this short time on one day in November 2017, we already get a sense of the mobility situation in the region. He used colors to represent different vessel types, and as an audience, we can immediately grasp the main patterns, the ferry connections, and the main shipping lanes that are characteristic for this region. So it becomes very clear to us that yes, there are definitely patterns there. There is value to this data that might be extracted, for example, regarding route recommendation or travel time prediction. If you go to the real far end, to the real fancy visualizations, of course, there's no limit as long as your budget allows for it. The flight data is a great example of a global data set which has really interesting patterns. This example shows for a day of particularly heavy traffic in the UK. So they illustrate how the day progressively gets worse and worse. First, the flights are quite regular, then they get delayed, and they draw them in yellow circles, and you can see how the planes have to go in those holding circles where they wait until they are allowed to land. And eventually all those red routes pop up because planes even have to be diverted. They cannot land in the airport that they were supposed to. So this is something that intuitively communicates a story. You get it, you know what it is about. And that's what people tend to expect when they think of movement data. However, I have to disappoint you. Once you get hold of real movement data, it's usually a completely different story. The question is mostly just boils down to how bad is the data and how much time will it take you to work through it to get to anywhere near those visualizations that we saw on the previous slides. So there's a real reality check that you have to go through and to understand your data before you can even begin to build any sophisticated visualization or even a predictive model like a machine learning model. This is just one example of things that regularly happen when you get movement data from somewhere. It will be an export from a bigger data set, so someone decides of where to cut it off, and they give you a certain area of interest, and lo and behold, there will always be trajectories that exit that area of interest, and then they enter it at some other point in time and location, and you will have effects like this where there is a huge gap which is just bridged by a straight line, because that's what any GIS will do. If you connect the consecutive points, you will get strange travel times, strange speeds on this connection, obviously. This can happen not just if the area is cut off somewhere, it can also happen if there's an area that for some reason is not included in the data set. Maybe it was already a mistake during the data collection process. So that's something that we always have to check for. Another thing which happens surprisingly often is that the IDs that you need to identify individual moving objects are not as unique as they should be. So if there's two completely separate moving objects running around with the same ID and you just try to connect the consecutive points, then you end up with this zigzag movement. And I know it now looks super obvious that there is something wrong with your dataset, but imagine that effect being hidden beneath hundreds and thousands of other moving objects. It will be really hard and it will be impossible if you just do it visually to determine that there even is a problem in your dataset. You will have to look at other telltale signs like unrealistic speeds, extreme jumps between locations to even find that. So you have to be looking for that issue. Something that is a bit more obvious, of course, is all this jittering that a GPS does when it stays at some location. If you have ever recorded yourself with a GPS tracker, you're probably familiar with that, even if you're just using the location services on your phone. When you stand still somewhere and look at it, your position still changes on the map. And that's exactly what we also observe in all the tracking data that we get. So it's not as simple if you want to detect where an object or vehicle was standing still for a given amount of time, you cannot rely on the speeds that are derived from the movement information because the GPS position is not actually standing still at all. It's always jumping back and forth, and there's these hairball effects at the stop locations, which we have to look at. Then there's even stranger effects happening, particularly with systems like the vessel tracking systems, where the locations are collected by antenna on the coast. So the vessels send out their location information and it's picked up by antennas on the coast. And the antennas on the coast slap a timestamp on it. So if the antennas on the coast are not perfectly in sync, then they will pick up the locations at different times and you will end up with out of sequence positions. And this again means that it looks like the object is jumping back and forth all the time along its route, when instead it's just a problem with those timestamps. Another thing that happens, of course, can be positions that are suddenly somewhere completely else. Null island is a great candidate. Null island happens often, but if the communication system is based on radio transmissions, as it's, for example, the case for the ship movement data, it can also just be a transmission error. And one of the coordinates could be wrong, and that can give you an off-course position that you have to filter out. And then somewhere along the whole processing chain, of course, it can happen that the digits are cut off prematurely and you get some zigzagging effects in your data, which again, they give you wrong direction information, wrong headings, and they also influence the speeds that you would derive from this kind of information. And even if technically there's nothing wrong with your system, there's always the possibility that something went wrong in your study design. This is an example that's almost 10 years old, and all we try to do is measure travel times along this intersection because they had changed some of the traffic light scheme and how it worked. So we sent a couple of people by car and a couple of people by tram, and we gave them GPS trackers. And we told them, yeah, just go over this crossing and we will derive the travel times from that and we will see if the measure made any difference. The only problem was this guy here in the middle, which is labeled route OW, just decided that he is not so fond anymore of going by car, and in the middle of the experiment decided to visit this park here right next to the intersection and walked around in it with his GPS tracker in his pocket, or I don't know exactly what he was doing. Long story short, the speed measurements from this tracker, of course, they had to be discarded and couldn't be used in the analysis. So technically everything was fine, but still the setup of the experiment was not perfect. So this brings me to my main point. Movement data is very rarely collected in lab settings. We get the data from somewhere. Even if we try to control everything, it usually does not work. There's always external factors that influence how the data looks like, what's going on in there. And quite often, it's not even our experiment that generates the data, but it's some other process that creates data for operational purposes, like actually running a fleet of taxis or ensuring the safety of vessels at sea or planes in the sky. So they did not collect this data for us to do any fancy statistical scientific analysis on top of it. That means also that the data quality is usually not ideal for the purposes of our study. And we have to deal with that because there is no other data. But we have to be aware of all the issues that are in the data. And this gaining awareness of what issues the data has and how we might be able to deal with those is a very, very time-consuming step. In the literature, that's acknowledged repeatedly. The different authors, they don't completely agree on how much time you actually need to get a grip of your data, but it ranges from anywhere between 50 and 90%. It's definitely one of the most time-consuming processes in any data analysis, and the same holds true for movement data analysis, of course. And part of the reason why it's so time consuming is that it's usually an iterative step, and it's not something that you do only once, because you start with the real world, you collect some data, or you get data somewhere, then you usually have to pre-process it, clean it before you can look at it for the first time. Then you will figure out some of the issues that are presented before. You might realize, okay, in the data pre-processing, I made a mistake, or the documentation that I was basing my processing on, they didn't get it quite right. It was probably outdated and I have to change something. And sometimes you also have to decide, okay, I have to collect different data. I have to get more data from the same sources or from similar sources. So it's this really iterative cycle, and you always get back to processing, cleaning, exploring, checking if your data is okay before you can even go into building any other more sophisticated analysis, the part which you then can write papers about or which you can sell to someone as a predictive model. And one of the key points in this whole exploration process is that you need to use visual tools. There is no use in just looking at some numbers, some statistics, some means, standard deviation, correlation. It's insufficient. And I really love this Datasaurus GIF because it shows exactly that. As a human observer, it's so clear to us that there are so many different patterns and it's changing so much. But the statistics on the right-hand side, they don't change at all in any meaningful fashion. And the same thing happens with movement data. If we don't look at it in its geographical context, in its temporal context, and observe how the movement really happens, we just don't get the complete picture. So exploratory data analysis is useful to suggest hypotheses. If you just get hold of a new data set and you have to figure out what is the potential of this data set, you cannot get around exploratory analysis. But it's also important to assess assumptions, to find out if the data set really has the potential to contain the information that you think it does and that you maybe need for your project. It's also important to find the right tools and techniques to handle the data. Because if you figure out, for example, that you have tools and algorithms in mind that require a certain characteristic from the data set, and then you realize, oh, only half of the trajectories in my data set actually follow these characteristics, and the others look completely different, then you either have to throw half the data away or you have to change your plan. You have to find other techniques, other tools. And in the worst case, as I mentioned before, the exploratory data analysis will show you that you don't have enough data. You need auxiliary data. So it also informs further or future data collection efforts. typical things that we do in exploratory analysis and tech tools that we need are first and foremost, of course, spatiotemporal queries. So we need to be able to find the movement data in a certain area at certain time. It's also very common that we want to find trajectories that are similar to each other, or that we want to join trajectories that are close to each other by some measure or other, either because they have same start and end locations, or because they really follow a same path for the whole duration of the trip or for parts of the trip. For a third thing that we quite regularly use is aggregations, and they quite often are grid-based. So the most classical one, which everyone starts off with, is of course the heat map. So you just throw the points on the map and you create a heat map. I'll discuss that a bit later, why yes, it's an okay starting point, but it shouldn't be the end of the analysis. There are more advanced grid-based and other summarizations that you can use for movement data. And these first three things are kind of a starting point. It gives you some data, but usually we want to extract more information about the movement. So we want to extract events. We want to maybe learn about places and how they relate to the movement. So it would be a typical use case to extract all the stops along a route, and then we can see where multiple stops appear and where there is a cluster of stops and which land use there maybe happens to be at that location, to inform all our knowledge and to connect places and movement behavior. And finally, another use case that we come across quite often in our work is the question of outlier detection. So that would be, for example, if a taxi drives against the one-way street direction, you might find out about this anomalous behavior either by comparing it to the map, to the network, road network itself, or you could also find out about that by comparing it to other historical data. So even if your road network data is outdated, maybe you could still find out that 99% of the cars only drive in one direction, and you could flag the one that is driving in the opposite direction automatically using outlier detection. What are the tools for this movement data exploration now, and particularly what are the concepts that are usually presented to deal with this kind of data? And the most classical visualization concept is certainly the space-time cube. And I have here this example of a rotating space-time cube, which gives you a bit of a better impression of how it works. It's just simply space on the X and Y axis, and on the Z axis you get the time. Which makes a couple of interpretations possible. So you can see by the inclination of the slope how fast the object is moving. If there would be a vertical line, you would see that the object was stopping at a certain location for a given time, and then it might have continued its route. You can also see that in this case, the object is returning to its original location at the end of the trip. Of course, this scales also to a couple more objects, so you can plot multiple trajectories in a space-time cube, like here on the left. There's maybe a dozen different objects here now, so it's already getting cluttered. But by plotting multiple trajectories in one space-time cube, you can find out when they were traveling together or when they stayed together at a certain location, maybe find out about rendezvous points, maybe find out if someone stayed longer and the other person left earlier, and information such as that. From the left-hand side to the right-hand side, what this example illustrates is that obviously, since it gets noisy so quickly, the space-time cube, we are tempted to aggregate it. And on the right-hand side, it's more or less a spatiotemporal heat map. So all the positions have been aggregated into voxels of position density, which gives you a better impression at which location there's a particularly high number of objects that are there at the same time. But it's already really easy to imagine if you had a little bit more movement, if you had a longer duration that you want to look at, this very quickly also will reach its limits. And you don't even have to go very far to reach those limits. There's this one data set that probably many of you are familiar with if you have ever looked into finding example data for doing any kind of movement analysis. It's the Geolife data set, which is mostly focused around the area of Beijing. It has some 25 million points in it. And if you try to plot those on a map just as is, there is just no way to extract meaningful information from that. Yeah, you can find out most of the information is in Beijing and a couple of trips are to other continents even, but you will not find out what's going on in Beijing if you just plot the points like that. You also won't find out what's going on in Beijing if you just render a heat map. First of all, you have to wait for that heat map to render, and depending on how strong your machine is, that wait can be quite a while, so get a coffee. And then what do we realize? The only thing that we actually see is that there's one location in the northwest where there is a lot of points, because I have to assume most of the participants in the study work or live there. So there's just a lot of points there, but we don't learn anything about movement in the city. And then what do we do next? We play around with the upper and lower limits of the color scale, and we try to find a setting which gives us a bit more information. So if we say the maximum value for the heat map should be a little lower, then we start to see other areas of the city pop up, and in this case they turn red. Like at the airport, there's also higher density of locations there, but also in the northeastern part of the city around those ring roads, there are some hotspots. But still, do we really learn anything about the mobility behavior? No. These heat maps are limited. We could filter them down to an hour of the day and maybe see which areas are more popular at night and which areas are more popular during the day. But what I want you to take away is don't stop there, look into other aggregations. This is an okay starting point to check if the data is at all like you expected from its spatial and temporal distribution, but it's not more than that. What we usually then do is we connect the points, we create trajectories by connecting consecutive points. Even then, as you can see in the beginning of this animation, it's usually a big hairball and still a huge mess, and there's definitely more analysis that you have to do to get to the next step. And the one that's illustrated here is splitting the long continuous tracks into individual segments by trying to find those stop locations where the person or the vehicle spent at least a certain amount of time in a smaller area. And the next step is then to cluster those and to find the biggest clusters and how they are connected between each other. And this is the first time in this processing this data set that actually gives you some result that can be interpreted in a way that you can compare it with your previous assumptions. Like, does it make sense that the people are traveling from the north to this central location and also to the eastern side? Is the relation in any way realistic, or do we already realize that maybe this sample is not representative of the movement behavior, and that we have to be careful of how we continue in this process? Another thing we can do with the same data set, in the previous example, it was all about the origins and destinations. The other perspective that we can take is, how do people actually get from one location to the other? So how do the routes look like? So this kind of aggregation, which connects intermediate points along the road, gives you this information. It shows you what are the main travel routes. At the expense of course, looking at this, we don't get the information of where the trips actually start and where they end. So it's one of the tools in your toolbox. You probably need to use both to find out, to learn more about your data set. And there are so many things that we should be looking at when we get a data set, and that require different handling and different analysis. From one of the key dimensions of movement data is obviously the spatial resolution. Much of the data that we work with nowadays is GPS tracking. So you have an accuracy of a couple of meters, but you can also end up with data sets that are much, much coarser. In movement ecology, for example, people have to sometimes deal with much, much coarser resolution. Also, if you get data sets with just Wi-Fi positioning outdoors or Bluetooth records, or even cell phone network information where you only know at which antenna some phone is logged into the network, then you suddenly jump from a uncertainty of a couple of meters to an uncertainty of potentially kilometers. Another thing that of course makes a difference is how many dimensions you have. Most of the data will only be 2D, but there's a couple of data sets like the flight data which are 3D, which makes it that bit harder because a lot of the tools that we have, they are just not designed for working with three-dimensional data. So you will have a harder time finding tools that are actually suitable. The temporal resolution is also a huge issue. There is on the one hand side data with a very, very high resolution where you have positions every couple of seconds. And then there is data like from cell phone networks where you might not get an update about the location of a certain object for many, many hours. And related to this resolution issue, there's also the sampling interval, which affects how you can interpret the data, because a lot of the algorithms require that the sampling interval is equal, so that you have a regular interval size which is steadily, for example, at every second a new location or every minute. But in real world data sets, it's really rarely the case that you get a regularly sampled movement trajectories. Instead, they can be based on some rules. For example, in the ship movement data, a ship that is moving fast and is changing direction will have to send its updates, location updates, at a much, much higher frequency than a ship which is currently laying at anchor or traveling really slow and on a straight route. They will only send one position per minute, while if they are fast and changing direction, they send a position every 2 seconds. So if you create a heat map, for example, of these positions without resampling them, you will totally overrepresent the fast moving ships that change direction, and the slower moving ships that just move straight will be underrepresented because they have such a different sampling intervals. Another thing that affects which tools we can use are the constraints that are enforced on a certain movement. So if you have taxi movement data, of course, that will be constrained to a road network, and you can use that information. It's really useful to know this taxi had to be on a road network somewhere, or maybe on a parking lot. But if you get flight information or ship movement data or animals moving somewhere, for example, migrating birds, then they are not constrained by a network. Yeah, they might still be constrained by some geographic effects. Ships obviously shouldn't try to go on land, for example, but it's not the same thing. You cannot use previous knowledge about a street network to deal with the data. There's also some different movement models which are used in collecting the data, and which are also quite essential for the way we look at the information. There is the one type of movement model where the tracker is attached to the object that is moving. So that is all the cases of where you have GPS trackers attached to someone, or also the Wi-Fi tracking. And on the other side, you have movement models where you only have some certain checkpoints. And at the checkpoint, you can detect whether a certain object passed. So that would be, for example, camera traps in movement ecology. You might have pictures of the same individual, and you have to identify them at different locations to even find out, for example, the habitat size of a certain individual of a certain species. So that makes a huge difference. There's also a difference in how the tracking system itself is set up, whether it was designed for the purposes of tracking, like in a taxi center, the system is of course set up for tracking because the taxi driver wants the center to know, to be able to send them to the nearest customers so that they can efficiently do their routes. but other tracking systems are not built for the same purpose. The ship tracking system is enforced for safety reasons and for monitoring. But as a vessel owner, as a captain, for certain purposes, I might not be very interested in being tracked. So for example, if I decide to go fishing somewhere where I maybe shouldn't be going fishing, I might be tempted to switch off my tracking system, or I might be tempted to supply it with some information that maybe is not so correct, just to cover my tracks. So when we interpret the data, we have to know about that. Are the people or the objects being tracked incentivized to maybe fudge their data a bit? Is it possible that they turn it off if they want to? And yeah, this goes also directly into the issue of privacy, of course. So depending on the privacy, we have different options of how to analyze the data. And quite often we might not be able to do all the kinds of analysis we want because of some pre-processing step that has to enforce certain privacy rules and therefore will discard information which could be traced back to certain individuals. And in the end, picking the right tool is also a question of data set size. Unfortunately, that's very true. There's a lot of tools which would be nice to use, but they don't scale to really large data set sizes. And we just have to put up with that. The important thing is there is no right tool for the job. There's no right tool for all the jobs, no one size fits all. We always have to look at the combination of these different dimensions and then reevaluate what kind of tool we want to use, which algorithms, which approaches are necessary. And that's also why this slide with potential tools that you might want to use when you work with movement data is getting more and more full and messy, and there's not this one clear answer. Depending on what your focus is, you might be more familiar with one or the other area of this chart, whether you come from the spatial domain where there is desktop GIS applications and web mapping libraries, or whether you're from the general data science side where you have time series data that you're analyzing quite often with Pandas or with R scripts. Or whether you're working in the big data domain where you're familiar with Spark and some of the more distributed computing libraries that are out there. And what I want to do on the next couple of slides is I want to show you some combinations that we are using in our research, and I want to give you insights into how they are suitable for certain tasks, where their limits are, and hopefully give you an impression of where you could start your own journey if you have to work with movement data. So the traditional approach that my team usually followed over the last 10 years for our applied research projects is, of course, we get movement data from somewhere. We also collect all kinds of other spatial context data. And then we have to look into this data set. We have to explore it. We build hypotheses. We have to check the assumptions that were formulated probably in a project proposal that was written before we had access to the data. And then you have this iterative cycle of building models, training machine learning models, applying them, doing predictions or anomaly detection, things like that, and evaluating them and going back and forth until you have the research projects, the results, the algorithms, the models, which, to be fair, usually doesn't mean that you have reached a perfect state. You just have reached a state which has to be enough because time's running out and you also have other things to do. So this time's running out will be essential because we want to work efficiently. One of the tools that I've been using the most in almost all projects is a combination of desktop GIS and databases. So for me, that's QGIS and PostGIS. And I think this is a really strong combination for a lot of projects because it gives you a lot of options. It gives you a lot of rendering options. The cartographic capabilities of QGIS are quite strong and flexible. So you can spend a lot of time fine-tuning those, really trying to discover the nuances. Also, the rendering performance is quite okay, so you can visualize rather large data sets, and you have an easy time adding spatial context, either from other data sources that you get within a project, or just simply base maps from web services, OpenStreetMap, anything like that is easy to integrate. There's also a lot of regular spatial analysis tools that are already contained within the library. So you don't have to go to all different lengths to use different tools to do others analyses. Usually there is no programming skills required, which is another big plus, and it's relatively easy to set up. And even if you run into trouble, there's a big community that is able to help and provide feedback if you have any obstacles that you can't overcome yourself. The main issues when it comes to working with movement data, however, is that for historical reasons, desktop GIS have very limited support for the temporal dimension. So there's a couple of things that you can do, but there is really few tools which really deal with time as efficiently as it does with the spatial dimension. And there's certainly very few functions that really provide dedicated functionality for movement data. One of the things that Martin mentioned in the beginning is a tool for visualization that I developed 10 years ago, which is called Time Manager. And it's been used by all kinds of people, for example, in this case, to visualize public transport data. And it's really neat as a first exploratory step to give you an impression of how the movement in a certain area looks like. You can style the movement locations depending on how old the position is and how fast the object move is on some attributes of the moving object itself. So there's a lot of degrees of freedom here. But we also have to acknowledge its limitations. It's not an analytical tool, it's a visualization tool, but it doesn't give you answers beyond that. You can, as a human, look at the patterns that you find, but it does not find any of the patterns by itself. It's not a pattern detection, doesn't contain any pattern detection mechanisms. It doesn't contain any stop detection mechanisms. It's a visualization tool. One of the newest developments when we're talking about this combination of QGIS and PostGIS as a database backend, which I definitely recommend using if your movement data gets larger. Otherwise, all those animations with Time Manager or the new temporal controller will be rather slow. So you have to have a backend that supports indexing on the temporal and the spatial component, and PostGIS is very suitable to do that. But until recently, at least, PostGIS didn't have any dedicated movement data support beyond basically 3 functions that someone developed a couple of years back. This has changed. There's now an extension that builds on top of PostGIS, and it's called MobilityDB. And what it does is it really gives you trajectory objects that can be stored in the database. And it's an open source extension. It tries to implement one of the newer standards by the Open Geospatial Consortium, OGC, which is called Moving Features, and particularly the Moving Features Access standard. So if you're familiar with standards in the GIS world, we usually have the simple features standard. And simple feature access defines how to compute intersections and touches operations and all the other operations that we do on simple features in all the GIS. So this new moving features standard tries to be a similar thing for movement data. And yeah, I already mentioned they build on top of Postgres and PostGIS to put the movement data in. And this standard is quite ambitious, because one thing that I haven't mentioned so far is that it's not even clear that movement data has to be limited to point locations. There's also some examples of movement data. For example, if you're tracking a storm front or a flooding event, then you have an area that might move or change its extent over time. And that's something that this standard also tries to cover. So it's pretty extensive, it's far reaching. It currently has a couple of issues. There's as I've experienced very little public awareness of it. So that's something I try to change. It also contains a couple of different standards for how to encode the data. So how do you actually store this information about the movement data? Those include text representation in CSV. There's also an XML version and a JSON version. And they're all slightly different, unfortunately, I think. And there's a couple of ambiguous definitions in the standard itself, which is an issue because there is so far no reference implementation. So there's nowhere to look up what the authors of the standard actually meant by some of those definitions. If you're interested into learning more about this standard, we have this discussion paper out. We wrote it in summer, and I recently presented it at the OGC working group meeting on this standard. It's a work in progress, but I think if it's successful, then it will help that all the different tools which are currently being developed for dealing with movement data have a common vocabulary to talk about the functions that we want for movement data and how different effects should be represented in movement data. One of the tools where I would have hoped to build on this standard is Moving Pandas, the Python library that I started developing late 2018. Basically, I waited a long time for someone else to do it, but that didn't happen. My first goal was to create directly a QGIS plugin for handling movement data in QGIS, because as I mentioned, Time Manager is great for visualization, but it doesn't give you any analytics. So I wanted to bridge that gap of the analytics part. And while working on this plugin, I'm thinking about all the things that I would need to do to get it working. I realized, hold on, probably you should start from the core functionality and you should pull it into its own library, which could exist and live outside the context of QGIS and could be used by others who don't want to bother with desktop GIS eventually. So I started a separate library, called it Moving Pandas, and the reason why it's building on Pandas is because Pandas and its GeoPandas extension bring together two essential things that we need for movement data. It brings together really good time series handling from the Pandas side, and it brings geographic data types from the GeoPandas side. So in Moving Pandas itself, I can focus on the things that are specific to movement data. I can focus on just implementing this trajectory data type and all the functions I need to deal with it. And I don't necessarily have to bother about the time series handling myself, for example, for interpolation. And I don't have to bother about handling coordinate reference systems and reprojections because that is dealt with by GeoPandas and the underlying libraries. So obviously, since we are now crossing into the realm of programming libraries, if you want to use Moving Pandas, for example, in your Jupyter notebooks or in any other application that you're building, this will require some programming skills. Since it's Python, I think the barrier to entry is rather low. There's also a large set of tutorials already in the repository, which you can try and familiarize yourself with the concepts, but still you will have to write some code. Currently, the community is obviously much smaller than it would be if you use QGIS or PostGIS, but I'm very optimistic that it's growing, and I already see an uptick in pull requests, questions, issues on the repository. So I think we're definitely getting there. I'm very optimistic. On the rendering capabilities, the cartographic representation is far less powerful, obviously, than it would be in QGIS. While we can visualize some basic patterns in Jupyter notebooks using different libraries for plotting like hvplot or even matplotlib itself, there are a lot of things which those libraries currently cannot do, and probably they will not attempt to ever cover the same cartographic feature set that a desktop GIS application can cover. So I think there is still value in eventually bringing these analytical capabilities into QGIS. Also, one last thing that I definitely want to mention is that it's currently rather slow for big data sets. That's also one limitation which I hope that I don't have to address myself. Luckily, there is really a strong push by the Pandas and GeoPandas community to get GeoPandas work on distributed setups. So currently, most of the things are just running in one core. That's why you're limited and everything is kind of slow, and you look into the task manager and you see, yeah, great, it's only using one core. No surprise that I'm waiting here forever. But there are efforts to do distributed GeoPandas computations, for example, with task. And I'm hoping that improvements in GeoPandas will eventually also speed up moving pandas. I mentioned that there's lots of tutorials. I really encourage you to have a look at them. Here's just a couple of screenshots to get you interested. For example, I often mentioned it's essential to be able to extract stop location from trajectories. So that was the previous example. It's also essential to have ways to reduce the dataset size. So there are functions for generalizing the trajectories. This particular animation also shows you that in Jupyter notebooks, you can create some small dashboard applications, interactive applications, which enable you to play with, for example, in this case, the generalization parameters, and you can watch how different tolerances for the Douglas-Poiker algorithm, for example, affect the eventual generalization results, which is really neat. It's just a couple of lines of code with these libraries. And you can also extract great aggregate visualizations like the ones I previously showed you for Beijing, where you saw the routes and how popular they are. Here, the same approach is applied to data from Migrating Birds. So here you can also see which routes do those birds usually take. The leftmost map also shows you one of the shortcomings of the visualization, because there is no way to plot the lines in an offset fashion, so I cannot just move them a bit to the right or to the left to better visualize the movement directions like I would do in a desktop GIS. Instead, both movement directions are plotted on top of each others. And currently, I'm limited to opening feature requests for maybe getting this feature implemented in the future. So, since this is all well and good, but unfortunately limited to small data set sizes, and not all our projects are happy with just dealing with small data sets, we need a plan B if the data sets are large. And our current plan B for large data sets evolves around Spark, evolves around the language Scala, which is one of those JVM languages similar to Java. And we use, instead of PostGIS, we use GeoMesa as a storage system. So it gives us a distributed spatiotemporal storage and faster access to large data sets, and also much faster importing of data into this database. For the visualization, we have to make use of many more tools for interactive exploration, notebooks such as Apache Zeppelin, QGIS we also use, and GeoServer, which integrates with GeoMesa and gives you a WMS and WFS connection to the data stored in GeoMesa. Specifically, that's our stack, how we have designed it so far. There is in the bottom, the HDFS Hadoop distributed file system, which distributes the data over all the compute nodes that we have in our cluster. Our cluster is in-house, so we really have the metal in our server room, and we manage it ourselves. On top, there is a key value store, which is not aware of any spatial or spatiotemporal magic, but this is added by GeoMesa. GeoMesa gives you the spatiotemporal indexing capabilities and functions on top of this data store. And with that bridge from the big data world, we can go into the spatial analysis and GIS world through GeoServer into QGIS, for example, and time manager visualizations. So this is very scalable. You can put additional machines into the cluster and you get more computing and more storage space. The spatial temporal indexing is really fast. The spatial support is good because GeoMesa builds on all the standard GeoTools libraries. That's also why it integrates so well with GeoServer. Therefore, it supports the OGC standards, and the data exchange is rather smooth. The downsides certainly are that the learning curve is very steep. You have a lot of moving parts here and a lot of tools which you have to install in the right versions, and you have to be able to operate them to really get your money's worth out of it. Also, the community is still rather small, and there is right now no particular movement data support. So everything we have in those spatial temporal indexes is general purpose spatial temporal indexes. It could be any kind of spatial and temporal information. It doesn't have the inbuilt knowledge that some observations belong together. They all belong to the same moving object. It cannot take any, it doesn't extract any advantage from this kind of information. One of the projects we are using this setup with is for the movement data analysis for ship movement data. And the dataset size there is, as you can see in this graph, around 10 million records per day for multiple years. So in this graph, we only have the first 1.5 years. If you sum it up, you get to around 7 billion points. That's a neat little data set. Also, each of these points has 22 attributes stored together with the coordinates. So yeah, it doesn't load in QGIS anymore. However, what you can do, as I mentioned, since we have this data in the GeoMesa distributed storage, and we can publish it through GeoServer, we can consume the WMS from GeoServer, and we can visualize the WMS map in QGIS. And Time Manager has an extension of using the temporally enabled WMS. So what you can see here is basically QGIS Time Manager sending off a spatial temporal WMS request for a certain area for a certain period of time to GeoServer. GeoServer fetches the information from GeoMesa and renders it here in our desktop environment. And this is the real speed. I didn't speed it up at all. This is just the screencast from probably 3 years ago. No particular tricks here. And you can see when I change from 1 minute to 10 minutes time frame, how we can see multiple positions for every ship, and which gives us some information about the historical movement, about how fast the ship might be moving or if it's standing still. All these kinds of things are possible with this little stack. And this also had the example of the basic heat map, which I already mentioned. Yeah, it's fast, but it also has its limitations. To get around these limitations, and to learn more about the data set, we developed a different kind of approach, which is still grid-based, but for each grid cell, we collect much more information than just the density of the positions in this cell. We called it the Massive Movement Model, or M3, and it collects all kinds of statistics for every cell of the grid. For example, it distinguishes the different ship types, and it also distinguishes information such as movement direction and movement speed. We are training that on our in-house cluster, which had 8 nodes when we took these numbers. And you can see the run times training this model, going through all the billions of records, is something between 15 minutes and 1.5 hours. So that's certainly something that you can do repeatedly multiple times during your project duration, and it doesn't take away valuable time that you then do not have to do your predictive modeling. When we first tried to do this on just one machine, distributed multi-threaded Java processing, we were much more limited. We usually had to run a much smaller area for over multiple hours. So usually at the end of the day, you decided, okay, let's try this parameter setting. Let's start it. Let's go home. next morning we come back. We hope it didn't fail. We hope it produced results, which we can then spend some time analyzing, and probably realizing that one of the parameters probably wasn't okay, or there's still some bug in it. But basically it meant you could have 1 or 2 iterations per day. What can we get? What can we see? Just a couple of examples now from the massive movement model. Here on the left-hand side, there's cargo vessels, and the bigger the circles marker, the more cargo vessels there are there. So this is basically the heat map part of the massive movement model. But in addition, you get information about the speeds. So you can see in blue where the vessels travel faster. You can see in red where the vessels travel slower. So these are usually ports or anchoring locations. Compared to the right-hand side, there you have passenger vessels. You can see this completely different routes. It's really clearly divided between stopping and fast movement. So ferries, obviously, they're usually faster traveling. Completely opposed to fishing vessels, there are almost no blue locations. They are much, much slower. They spread everywhere, wherever they are allowed to fish. There are some areas which they don't enter, probably because they're not allowed to fish there. And the fourth example that I added here for comparison are the pilot vessels, which usually don't leave their port area. They just go out a certain distance until they meet whomever ship they have to go to. If you zoom in even further, there's more information that you can also visualize. For example, here we have also the direction of the movement, which is illustrated by the pointy arrow. So you can see there are traffic separation schemes in the sea. Ships are usually move one direction on the one hand side, other direction on the other side, except for fishing vessels, of course, again, which they just do their turns and collect the fish. We even applied this data in the paper to the movement in urban settings. As I mentioned before, in urban settings, you have other options. You could also just snap the locations of the taxis to the street network. But this just is to show that we can apply this movement model also to other data sets, and we can play with different levels of resolution, and it gives you a different impression of the data. Beyond what we are doing, there's also a lot of other groups who are trying to improve the situation of movement data analysis in the big data world. There's just one project which I want to highlight because I heard a recent presentation at ApacheCon a couple of weeks ago, and that's Apache Sedona. You might know it under its previous name, which was GeoSpark. So that's more descriptive of what it really does. So it's a spatial extension for Spark. They recently rebranded to Apache Sedona, and they aim to include functionality dedicated for trajectories. So it's not a done deal yet, but they certainly have the ambition to do that. So there's a lot of challenges and research areas that still remain wide open for anyone who wants to get into this domain. There's the real huge challenge of variety, all those different movement data sets. There's increasing challenge of velocity and volume, so we still need efficient trajectory indexing, which is really available for researchers to use. There's a lot of publications, but there's really little that is implemented. There's also the huge issue of validity and veracity of the data. I already mentioned sometimes the person being tracked might not want it to be, might have a reason to bias the data. Also, you might not be collecting representative data because of the people who take part in your studies. So that's always something to be aware of when analyzing the data. And for visualizations, there's still huge issues of dealing either with large data sets or even medium data sets. It can be really difficult to find well-fitting visualizations that reveal the patterns that are in the data. And privacy continues to be a huge issue in almost all parts of mobility research, except for a couple of minor examples maybe. And that's because tracking data is so hard to anonymize if you want to ensure that it's still usable in the future by other researchers. I would go so far as saying that most anonymization processes destroy a lot of future potential of the data set. I don't think there is one anonymization process which can be safely applied and still ensure that the data is applicable, still valuable for research. I think we will need a couple of different anonymization procedures. Depending on what you're planning to do with the data in the end, you will apply one or the other. But again, I think there will not be one size that fits all. And same applies for the tools for exploratory movement data analysis. We have to find some ways to bring privacy considerations into those workflows, but how we can do that and still get to where we need to go is a huge issue, which I hope we can explore in the future. So with that, I hope I gave you an overview and an inspiration of what tools you might want to use, and I'm really looking forward to your questions and comments. Thanks.
Thank you, Anita. That was absolutely amazing. We would all clap if we were in the same room.
Thanks.
Everyone, feel free to ask your questions in the chat, and I will go through them and read them to Anita. So we will do Q&A in this way to have it slightly more managed. I will start with the question from Levi Wolf, who's first of all thanking you for your talk, and then he says, I wondered if you could speak a little bit more generally about how the process of writing a library like Moving Pandas has changed your thinking, either in research and teaching. He also adds that he knows that his involvement in Python and GeoPandas has changed this.
Well, it wasn't my first rodeo, let's put it that way. I've been maintaining the Time Manager plugin for 10 years, so I kind of knew what I was getting myself into. That's also why I waited so long to do it. I wasn't really fond of the idea of picking up a new project. So I'm quite happy that Time Manager is now preceded by the temporal controller, which is part of QGIS itself, so I can focus myself on moving pandas. But it's really hard to build something that others should use. As long as you build something for yourself for a specific project, you can be very specific, tailor it to the requirements of this one particular data source. You don't have to focus so much on documentation because you think you will remember what you did when you get back to it. But it really makes you think of what are the really important functions that you need to cover. And that's also why I really hope that the standardization processes will get somewhere and that we can find a common language and a common data model to represent movement data and to work with it. Because right now, if you go through the literature, you will find so many different terms which all describe either the same thing or you have the same terms for different things, like what is a track, what is a route, what is a trajectory, what is a sub-trajectory, a trajectory segment. All those things, you don't necessarily know what exactly does the author mean if they don't have nice examples to go with that. Sometimes it's even contradictory. So it's all so new. We should pool our efforts together and build something that we can all reference.
Great. Okay. Daniela asked even during the presentation, so you probably answered partially this. For this big data analysis, what is the main resource of the data?
Resource of the data, so the data source. For the movement data, for the ship movements, there are some public data sets that you can access. For example, the maritime authorities of the US and of Denmark, they publish historical data sets, big dumps of CSV files and personal geodatabases, I think it's in the US. For Finland, there is even an API with live data which you can access. Then there is some hubs, AIS hub and for ship data and ADSB hub for flight data, which are like a membership model. So you have to put up your own antenna, collect some data, then you put it into the hub and you get everyone else's data out of the hub. And of course, then there are commercial data providers who are more than happy to sell you the data if you can pay for it, or industry connections.
Great. Alon Sage, or I'm sorry for pronunciation, asks what kind of models or algorithms can these tools make except explanatory visual models?
Well, that's a very broad question. I think out of the box, there is very little that you get beyond exploratory visualizations from most of the tools. So if you want to build, for example, a travel time prediction model, I'm not aware of any of these existing libraries which gives you something out of the box. Things that do exist, for example, besides moving pandas, there's also another Python library called scikit mobility. They include some measures about how privacy sensitive the information is, and they have some KPIs for assessing the privacy relevance of the data. You also find some tools that give you access to simulating movement data. Lots of them are either from the movement ecology side, or it could also be from urban cities research, where they are modeling how agents might move through an urban network. So you get these dataset generators on the other side. But really, pre-built tools for predictive analysis are very rare and far between.
Thank you. Another question, have you tried to apply these tools to indoor mapping?
Indoor mapping is something that I don't come across very regularly. So you would have a couple of other challenges that come with that. Mostly, yeah, I think many of the things would be applicable. Again, you verge into the realm of 3D analysis. At least you have to deal with different floors and how they are connected in your data. So I haven't looked into those challenges specifically so far, no.
You've mentioned that your hardware stack at the Austrian Institute of Technology is all in-house. Do you have any suggestions or advices for those who are setting up these stacks in cloud environments? Do you have any experience with that?
I have tried a couple of things, but it would be too early to say that I have one preferred solution. I quite like, for just playing around and for ease of use, Databricks solution. You can quite easily get a test account and play around with it a bit. I have a blog post which shows some ways of interfacing GeoPandas with Spark for running it on Databricks. But I haven't used any of the cloud solutions for significant size of data, because yeah, it quickly gets really expensive. So if we would want to store our terabytes of movement data on a fast storage in S3 or wherever, it would get really expensive really quickly. So I can't just do that on a whim.
Yeah.
So no endorsement for any of those providers so far.
Can you elaborate a bit about differences between moving pandas and scikit mobility?
Sure. Basically, they sound similar, but they're not similar at all in the end. They cover completely different use cases. From the technical side, the main difference is that scikit mobility builds only on pandas and not on geopandas. So they do all the coordinate handling themselves. They also do the plotting themselves. So you will not get the same built-in and automatic visualization capabilities that you get in moving pandas, where the information is basically stored in a geodata frame and you can do all the plotting that you do with a regular geodata frame. Also, they focus a lot specifically on human movement data and on generating movement data for their urban data analysis. On those privacy questions that I mentioned, so they want to extract those measures versus for moving pandas, my focus was to really allow the user to do this exploration and to visualize the data in many different ways and get a better understanding of the data in a more interactive setting and not just computing some values that you need for a publication. I think those are the key differences on the user side. On the developer side, besides their choice not to use GeoPandas, it's also slightly different setup, bit fewer unit tests, and I don't know how active the current development is. I know that there is a couple of commits every now and then in the repo, so it's certainly not abandoned, but I don't know what the long-term plans are.
Great. Is it possible to integrate or use moving pandas with QGIS by either using Python console in QGIS or graphical model builder?
Yes, it's definitely possible via the Python console. So if you install moving pandas into the Python environment of QGIS, then you will be able to import it for sure. Eventually, I also want to build a plugin again. The main issue right now is, or always is, how do you install all the necessary dependencies on different operating systems? That can be a bit tricky. Currently, moving pandas installation works quite well if you use Conda. But yeah, that's not so low level that I would be comfortable with requiring that from every QGIS user who wants to use the plugin. So I'm a bit torn between simply including the whole of moving pandas with the plugin. And so you have all the dependencies included in the plugin when you download it, versus trying to find a way of how to enable users to install the dependencies by themselves. But yeah, the end goal is definitely to go back to this integration and to bring all the functionality from moving pandas into QGIS. Right now, I would imagine it's a bit of a rough ride. I have a couple of blog posts already up which describe how to go from QGIS layers to geodata frames. So the conversion process is clear between the two and it's not very challenging. But you also have to be able to call then all the functions in in moving pandas in a comfortable way. So what we probably want to do is add all those functions to the processing toolbox. And that will probably be a lot of work, which I hope we will be able to tackle in the future, particularly if a couple of more people join in.
I assume the biggest challenge with dependencies is GeoPandas, right?
Yes, GeoPandas has a lot of dependencies. Also, the plotting libraries which I chose, HVplot, HoloViews, they also bring their own dependencies, which I'm currently working through if there's a way to pull those out again and just have them as optional, because for the integration of moving pandas into QGIS, we don't need those other plotting libraries necessarily because the visualization part will be taken care of by QGIS. But right now, all the dependencies are mixed together and it's one package deal, which doesn't make it any easier. But yeah, there are some GeoPandas dependencies which are really hard to install,
And
particularly on Windows.
I hope I have good news for you that GeoPandas is working on this issue, and it's possible that one of the future releases will depend only on geos regarding C dependencies, so it should help
That
with
would
this.
be awesome.
Okay, another question from Emanuele Rossetti. He's wondering if you could speak about how to handle the variation in the acquisition of data through time for historical analysis. For example, addition of new AIS terrestrial receivers or new satellite AIS receiver, and therefore increase in traffic in a specific area.
Yeah, that speaks to an important issue, of course. It's probably for AIS data, I don't even think it's such a huge deal, because you will have, if you add a new receiver, then you will either increase your coverage because you can suddenly see some ship movements that previously you couldn't observe at all, or you basically add more records to an area which you've previously already seen. So you would see effects for sure on analysis such as movement density, if you have heat maps or ship density measures that you do in your analysis. It probably won't make a large difference if you look at counts such as distinct vessels for an area, because either you did not observe the area previously, then you have nothing to compare it to, and suddenly you do have observations in this area. But I can imagine in other environments, it's really a huge challenge to deal with changes in the setup, particularly if you have checkpoint-based systems like a mobile phone network where the antenna configuration can change, and suddenly the ID of the antenna might be reassigned to a different location. Then you really have to deal with, break it down to maybe abandoning the IDs and go back to the geographic location at a certain time. But it certainly gets messy, particularly if the changes to the network are not very well documented and you kind of have only snapshots of the situation for particular points of time. And in between, you can never be sure if the positions are actually correct. So that's one of the downsides of this kind of data.
Okay, we are getting close to the final questions. Can we use moving pandas only to do a proper detailed exploratory data analysis on movement data? Or do we have to skip to QGIS or to other tools?
That's a trick question. I think a bit, as I mentioned, one of the main issues is that it does not scale to really large data sets. So I think once you notice that the rendering in the Jupyter notebook gets too slow, it's probably one point where you should reevaluate if you want to do the whole exploration in moving pandas and the Jupyter notebook, or you might decide to just do some pre-processing steps using moving pandas, then save the augmented data in PostGIS, which is easy enough with GeoPandas to store the geodata frames into PostGIS afterwards, and then do the exploration in QGIS, where you have way more cartographic capabilities. So as both toolings enhance, I think there will be less and less reason to switch from one to the other all the time. Right now, I see many cases in where I and others might want to change between one setup and the other. So no, I would not say that you can do an exhaustive exploratory analysis of larger data sets purely in moving pandas right now.
Great. Short question. If we can get the references you have used in the presentation from somewhere.
Yes, I can definitely share them. I'm planning to put the slides online and I will add a reference list to it.
Great, thank you. And there was another fairly technical question regarding the in-house cluster. How many people have been working to maintain such a cluster, and how much approximately does that cost if you have this kind of knowledge? And do you have an external support, or do you do everything in-house?
We don't have external support. We are very glad that the GeoMeso developers have been very responsive via Gitter whenever we had issues in the beginning, learning how to set up the whole stack. We are a rather small team, so there's currently just 5 to 6 people, depending how you count it, of us who do this data exploration work. And no one is working on maintaining the cluster full time. So it's something that has to be done on the side as a part of research projects that we are currently running. So there is not really a rundown of what it would cost us specifically to host this cluster. It's something that we need because it wasn't possible to deal with the amounts of data that we had on even the largest server that we had for processing. And that's why we started this effort. But I don't have the numbers to tell you what it really costs to maintain this thing.
Yeah, and the final question is, do you think it is possible to go ahead with detailed AIS analysis using PostGIS only? That you did mention that big data framework may be better.
I think we, in our efforts, did not reach the limits of what PostGIS can do, for the simple reason that we never attempted to do a distributed PostGIS setup. We didn't use any of the, is it Citrix solutions for a distributed PostGIS setup, where you would also be able to speed up your I/O times and your processing times. Also, recent versions of PostGIS have parallel processing capabilities, evaluation of spatial indexes on multi-threaded ways. So it's also getting faster and faster all the time. And the limits of when you definitely have to change away from a conventional database, they keep shifting into larger and larger dimensions all the time. It really comes down to what you feel more comfortable with and what you want to invest your learning resources in. If you think that learning the big data technologies is worthwhile for you, then I would look into that. But if you have someone in-house who already knows how to set up a distributed Postgres database and how to maintain and update that and really tune it, then probably for a very long time you don't need to go into the big data world at all.
Okay, our time is getting short, so one final question. Are you aware of any good libraries for this type of data in R?
It's really hard to get an overview of R libraries. In my publications, in the reference list, you will find some recent work. For example, just looking at movement ecology libraries in R, they found over 50 libraries which have been developed for dealing with movement data in movement ecology. And they try to classify them into what is more useful for which use case. But since personally I'm not very much of an R user, I haven't evaluated the general purpose movement data libraries and how far which one would be currently the leading one. I think if you're into R and looking for solutions there, people like Etsa Bibisma would probably be the first contact point. So everyone who's developing the spatial stack, SF and all those libraries for R, they will certainly know which are the most promising candidates right now for movement data in R.
Great. I think it's time to close this down. Thank you again a lot for your presentation and for detailed answers to all these questions. It was absolutely amazing.
Thanks again for having me. And
thanks for coming. And
if there's
thanks
any more questions, send it my way. I will send you the literature list so you can post it maybe together with the YouTube video in the description.
Yes,
Okay.
we'll do that.
Awesome.
We'll do that. So there will be a recording afterwards. Hopefully within a couple of days, we will be able to make it available and we will put it on our Twitter, Geo Data Science, I think. You will find it. Okay, thank you everyone. See you soon.
Thank you. Bye.